Hello and welcome back to another Algebra 1 video. Today we'll be starting Chapter 4, which covers everything on how to solve systems of equations. For this very first video, we'll be learning how to solve a system of linear equations by graphing. Let's take a look at what a system of equations is. So a system of equations is just a set of two linear equations that has a common ordered pair that makes both equations true. Now I'll go ahead and give you an example to illustrate what this means. Let's say we have this linear equation, y equals 3x minus 3. You can graph this on a coordinate plane, and let's just say, for example, that I choose the point 2, 3 that lies on our line. Let's say we have another linear equation, y equals negative 1/3 x plus 11 over 3. You can also plot this on a coordinate plane and identify that point 2, 3 on that line. Now, if you were to graph both of these lines on one graph, you'll see that they intersect at this point 2, 3. Now 2, 3 is actually the solution of this system of equations. It's this ordered pair that makes both equations true. Now you might be wondering, what does it mean to make both equations true? Well, let's just say that you plug 2/3 or 2, 3 into your equations. 2 would be your x value, 3 would be your y value. Now you can plug those into both equations. So first, y equals 3x minus 3 would give you 3 equals to 3 times 2 minus 3. That would simplify to 3 equals to 6 minus 3, and 6 minus 3 equals to 3. So your final simplified equation would be 3 equals to 3, which we know is true. So what this means is that 2, 3 is a solution of this equation. You can do the same for y equals negative 1/3 x plus 11 over 3. So I'll plug in 3 for y and 2 for x. So you get 3 equals to negative 2/3 plus 11 over 3. We have a common denominator, so just simplify the numerators. Negative 2 plus 11 would just equal to positive 9. So now you have 3 equals to 9 over 3, and 9 over 3 just simplifies to 3. So you can see that you get this same simplified equation of 3 equals to 3, and we know that it's true, so 2, 3 is also a solution of this equation. So you can conclude that 2, 3 is the solution of this system of equations because it makes both equations true. So for today's lesson, we'll be learning how to solve a system of equations by graphing. Let's take a look at our first example. We have x plus 2y equals 7 and x equals y plus 4. We're going to solve this system of equations by graphing. So let's take a look at our first equation. We have x plus 2y equals 7. Notice that this is actually in standard form, so you can use the Intercept shortcut. This is in ax plus by equals c form. So using the Intercept shortcut, you can find both the X-Intercept and the Y-Intercept, graph those 2 points, and connect them with a line. So I first found the X-Intercept. How you do that is you would just plug in 0 for y, so that y would cancel out. So once y cancels out, you see you have 1x equals 7. That would just simplify to x equals 7, so your X-Intercept would just be 7. You can do the same to find your Y-Intercept. How you would do that is just by plugging in 0 for x. So that would be 1 times 0 plus 2y equals to 7. 1 times 0 just cancels out, and you're left with 2y equals to 7. Divide both sides by 2 to isolate y, and you get that y equals 27/2, or that also equals to 3.5. So now that you have both of your intercepts, you can actually graph this on your plane. So your x-intercept would be 7 right here, and then your y-intercept would be positive 3.5, which is right there. And now you can go ahead and draw a line through your points. And there is your first line. Now we can graph our second equation. We have x equals y plus 4. This isn't in any form that we recognize, so we can rewrite this in either slope-intercept form or standard form. For this example, I'll just do standard form, which is ax plus by equals c, and c is going to be our constant. So I want to isolate 4 on one side and x and y on the other side. So I'll first subtract 4 from both sides. That would give me -4 plus x equals to y. And then you can subtract x, and that would give you -4 equals to -x plus y. And I just went ahead and rearranged y minus x into -x plus y to fit this format. But both are basically the exact same equation. So now that we have our simplified standard form equation, which is -4 equals to -x plus y, you can go ahead and find your x-intercept and y-intercept. I'll find my x-intercept first, so I would plug in 0 for y. Y would just cancel out, and you're left with -4 equals to -x. To fully isolate x, you want to divide both sides by -1, since this negative is still next to the x, and that would give you +4 equals x. So your x-intercept would equal to 4. Now do the same to find your y-intercept. You add -4 equals to -x plus y, except this time you're going to plug in 0 for x so that you can find the y-intercept. That would give you -4 equals to 0 plus y. 0 just cancels out and you get y equals to -4. No further simplifying to do, so now you have your y-intercept, which is -4. Now you can plot these on your graph. Your x-intercept is +4 right here, and then your y-intercept would be -4. And now you can connect your points with 2 lines. Now to find the solution to your system of equations, find this point of intersection right here. It's this solid point here at 5, 1. So you know that the solution of your system of equations is 5, 1. Let's look at this next example. We're going to solve this by graphing. We have 3x plus 4y equals to 20, and 3x minus 2y equals to 8. Now, I'm actually going to solve this first one and rewrite it in slope-intercept form. So the very first thing I'm going to do is try and isolate y. The first step I'm going to take is subtract 3x from both sides. So that would give you 4y equals to 20 minus 3x, and I just rearranged it to fit y equals mx plus b, which is our slope-intercept form. And we're not quite done yet because we still have a 4 getting multiplied by our y, and we need y to be completely isolated. So very last step is to divide 4 on both sides. So that would cancel out the 4 right here, and you would get negative 3 over 4x plus 20 over 4, which would just be 5. Now this is your final equation rewritten in slope-intercept form, and you can graph that on your coordinate plane. So you would have your y-intercept, which is positive 5 right here, and then you can plot other points using your slope. So in this case, we have a negative slope, so rather than rise over run, you're going to rise going downward, so you would go down 3 units, since this is again negative slope, and then run 4 units to the right and plot this point right here. 2 points is sufficient, but if you want to be as precise as possible, you can plot a few more points if you'd like. And then I drew a line to connect my 2 points. Now you can go ahead and move on to your next equation. We have 3x minus 2y equals to 8. I'm also going to rewrite this in slope-intercept form, even though it's already in standard form, because I don't think the numbers would work out too well, especially if you do try to find your x-intercept. 8 over 3x wouldn't really work too well, so I'm just going to rewrite it in slope-intercept form. First, I'm going to subtract 3x from both sides, and now you're left with negative 2y equals to negative 3x plus 8. You could have also done negative 2y equals to 8 minus 3x, but again, I just wanted to follow y equals mx plus b form, so I put negative 3x first. And once you've done that, you can go ahead and divide both sides by negative 2 to isolate y. So negative 2 would cancel, and you would get y equals to positive 3 over 2x, since negative 3 over negative 2 would just cancel out the negatives, and then 8 over negative 2, which would simplify to negative 4. And now this is your simplified equation. Y equals to 3/2 x minus 4, which you can now plot on your coordinate plane. First, plot your y-intercept, which is negative 4, and then from your y-intercept you can go ahead and count your slope to find another point. We're using rise over run since this is a positive slope, so I would rise 3 units, and then I would run 2 units to the right, and here's our other point. You can do one more point if you'd like, and here is our other point. I would recommend to keep on drawing points until you find a point of intersection between your 2 lines. So for this graph, or system of equations, it would be right here. Once I connect my line, I'll go ahead and find what our point of intersection is. It would be 4, 2. So the solution of this system of equations is going to be 4, 2. Here is another example. We're going to solve by graphing. First, we have y equals to negative 2 and y equals to 1/2 x minus 1. For our first equation, we see that we just have y equals to a value, so no slope. This is actually going to be a horizontal line. So you're going to draw a horizontal line through negative 2 on the y-axis right here. This actually goes back to chapter 2, so if you find that you're having trouble recalling any of the methods we graph linear equations, make sure to reference my chapter 2 videos. So I'm going to go ahead and draw a horizontal line here at negative 2 on the y-axis, and there is your line. Now you can go ahead and graph your other equation. This is actually conveniently put into slope-intercept form, which is again y equals to mx plus b. So since we don't have to do any rewriting, we can just go ahead and plot it on our coordinate plane. First, plot your y-intercept here at -1, and then from your y-intercept, go ahead and find another point by counting your slope. In this case, it is 1/2, positive 1/2, so it'd be rise over run. From -1, I'm going to rise 1 unit over 2, rise another 1 unit over 2. If you want it to go down, you can go down 1 unit and over to the left 2 units. And again, I recommend to draw as many points as you need to until you find a good point of intersection. In this case, it would be right here, which is -2, -2. Now you can draw your line through your points of the second equation and identify that point of intersection. Again, our solution would be -2, -2. So as you can see from all these examples, we're basically just taking our skills from Chapter 2, which is graphing linear equations, and trying to identify a point of intersection for our solution. Here is another example that we're going to solve by graphing. We have y equals to 2/3 x minus 2. This is, again, conveniently put into slope-intercept form, so I'll just go ahead and graph this using that form that it's given in. First, we have our y-intercept of -2, which is right here, and we have a slope of positive 2/3, so 2 would be our rise, 3 would be our run, so I would rise 2 units, run 3, 2 units, run 3. If you ever want to make any points to the left of your y-intercept, you can go down 2 units and run 3 to the left if it's a positive slope. And now that you have a good number of points, you can go ahead and draw a line through your points. And there is your line. Now we can get started on graphing our second equation. We have 2x minus 3y equals 6. This is actually in standard form. You'll recognize the ax plus by equals c form, so you can actually use the intercept shortcut. Now for some of our examples, even though our equations were in standard form, I rewrote them in slope-intercept form because the numbers didn't work quite well for the intercept shortcut. And how I determined that is just by taking the coefficients of both x and y and seeing if our c value, which is 6, can be divided by the coefficients. So 6 divided by 2 would work well, and 6 divided by 3 would also work well. So the intercept shortcut would work well for this equation. So let's go ahead and do that. First, I'm going to let x equal to 0 define the y-intercept. That would be 2 times 0 minus 3y equals 6. 2 times 0 just completely cancels out, so you're left with -3y equals to 6. Divide both sides by -3 to get your y value, and that would give you y equals to -2. Do the same to find your x-intercept, except now you're going to let y equal to 0. Y equaling to 0 would give you 2x minus 3 times 0 equals 6. -3 times 0 would just completely cancel out, and you're left with 2x equals to 6. Divide both sides by 2 to isolate x, and you're left with x equals 3. Now you can go ahead and plot this on your graph. Now let's go ahead and take a look at how this looks on our plane. So our y-intercept is -2, and our x-intercept is positive 3. Now if you notice, it's both of the two points that lie on our previous line. So if we were going to connect this line, we'd see that it's the exact same line as y equals 2/3 x minus 2. And if you were to rearrange this equation, 2x minus 3y equals 6, into slope-intercept form, you'd see that they'd be the exact same equation. So when you have a line that is the exact same as the other line, this actually represents a system of equations that has many solutions. So of course, since they are the same equation, if you plug in any point that lies on the line, it would be a solution of both of the equations. So there are many solutions in this instance. Let's take a look at this next example. We're going to solve by graphing y equals 2/3 x minus 2 and 2x minus 3y equals to 12. Let's first graph y equals 2/3 x minus 2. This is already in slope-intercept form, so you can just use the y-intercept and the slope to plot your line. Our y-intercept is -2, and our slope is 2/3, positive 2/3. So we're going to rise 2 units and run 2 units. So rise 2, run 3. And you can do a few more points if you'd like, just for a little bit more accuracy. And you can also do the same going to the left, except you would just go down 2 units and left 3. Now you can connect your points with a line, and there is your line for that equation. Now you can go ahead and plot your second equation, which is in standard form. We have 2x minus 3y equals 12. So I'm going to go ahead and use the intercepts shortcut for this equation, since again I'm checking whether the numbers would work out well when using the intercept shortcut. Look at the coefficients of x and y. In this case it would be 2 and -3, and see if you would be able to divide 12 by those coefficients. 12 can divide by 2 and -3, so I'll just go ahead and use the shortcuts, or the intercept shortcut. So first I'm going to let x equal to 0 to find our y-intercept. That would give me 2 times 0 minus 3y equals 12. 2 times 0 just cancels out, so you're left with -3y equals 12. Divide both sides by -3, and now you have y equals to -4. You can go ahead and plot that on your plane at y equals -4, and now find your x-intercept by letting y equals 0. So you have 2x minus 3 times 0 equals 12. 3 times 0, or -3 times 0 would just cancel out, so you're left with 2y equals to 12, or 2x equals to 12, and now you can divide both sides by 2 to isolate x, and now you have x equals 6. So plot your x-intercept. Now connect your points with a line, and you'll notice here that the equations are actually never intersecting. They're both parallel lines, so parallel lines just means that they're never going to have any point of intersection. Whenever you have two parallel lines in your system of equations, there's actually no solution. This is because since the lines will never intersect, there'll never be a point where both equations can be true. So to summarize what we learned in today's video, when we graph a system of two linear equations, one of three things may happen. First, the lines have one point of intersection. This is what we saw in a lot of our examples, and this one point of intersection is the only solution of the system. Secondly, the lines might be parallel, and if this does happen, there is no point that satisfies both equations. That's because the lines never intersect, so there'll never be a solution. And lastly, the lines coincide, or the lines are the exact same. So since the equations have the same graph, there is going to be an infinite number of solutions that satisfy both equations. I'll go ahead and illustrate all the cases that we saw in today's video. Case 1, where you have one point of intersection or one solution, such as this one. Case 2, where you have two parallel lines and there's no solution, like this one. Or case 3, where you have the same exact line and there are infinitely many solutions. That is it for today's video. Thank you so much for watching. As always, all information regarding tutoring, additional practice, and lesson requests will be linked down below in the description box. If you ever want to contact me regarding questions about the lessons, feel free to email me at kaylin.david24@gmail.com. See you next time.